Michael Paul with us from the Department of the Earth and Science, Oxford University. He is one of the world's leading structural geologists and a pioneer in the Himalayan tectonics. His works focus on mapping, analyzing, and reconstructing how mountains build through the time with structural analysis, geochronology, and the field geology. Professor studied the Annapurna to Dhaulagiri range, Everest, and the MST zone, and his research on the mountain building, crustal deformation, and the India-Asia collision has significantly advanced the geological understanding. And he has earned several high-profile scientific honors, including the Marketian medals and many more. And he has authored and co-edited numerous books focusing on tectonic, particularly concerning on the structural evolution of the active belts. And we are truly grateful to him for taking his time to share the valuable knowledge, professional experience, and insight with us. Additionally, we extend our warm welcome to all the participants whose active participation will add a great value in this program. And we are confident that today's session will be both informative and inspiring. Thank you all for joining us, and we look forward to a meaningful and enriching discussion now. Now, without delay, I would like to invite Professor Michael to commence the session. And if any of the participants have any queries or the questions, then you can write it down in the ask at the end of the session. Now, the floor is yours, Professor.
Okay, thank you very much, Isha. And namaste to everybody in Kathmandu. And it's very nice to be with you, even remotely. Before we start, we've had a few technical problems with the PowerPoint. So Anuraj will be forwarding the slides at when I put a finger up. So if I keep putting a finger up, don't worry. It's just I'm talking to Anuraj. But thank you, Anuraj, and thank you, Isha, for sorting out these problems. Okay, what I was going to talk about today was give you a tectonic summary overview of the whole of the Himalaya, how you make a big mountain belt like the Himalaya on a very large scale. And I have quite a few slides, so I will go straight on to the next one, please. So I've been, in the last 2 years, I've been compiling a geological map of the Himalayas using hundreds of different mapping publications from all across the mountain belt. And the end product of the map is going to look like this. It's being drafted at the moment, and we hope that it will be printed in September, October. So by then it will be available for public use. It's going to be 2 sheets. The western sheet goes as far west as Afghanistan and as far north as the Pamir. And the eastern sheet will include all of Nepal, Bhutan, the eastern Himalayas, and south as far as northern Myanmar. So this is the all of geological processes revolve around getting the information down on a map, 3 dimensions using cross sections on a map. So this is the starting point for all of the geological interpretations. Okay, so this picture here shows all of the elevation above 5 kilometers altitude in white. And you can see that the Himalaya forms the southern margin of Tibet, the Tibetan plateau. It's a very, very long, linear and abrupt mountain range. I'm sure you're all very well aware when you come off the Tarai and in Nepal and you see the first of the mountains, well, that is the main boundary thrust, which goes for at least 2,500 kilometers along the whole strike of the Himalayas. And the Himalayas is actually a remarkably simple mountain belt. You can take a cross section across the Himalaya anywhere from Zanskar Ladakh in India to the west to Arunachal Pradesh in the east, and you will go through the same major structures and the same major zones all the way through. So outlining on the right are the main structures that we're looking at. The main boundary thrust in the south, which is the active fault along which India is under thrusting the Himalayas. The main central thrust, the South Tibetan detachment, and the great counter thrust to the north, which runs along the Indus-Yarlung-Zangpo suture. And the suture zone in blue marks the zone of plate collision between the Indian plate and the Lhasa block, or the collage of plates that make up southern Asia. In the west, this is also complicated by the very large Kohistan Island arc, Kohistan-Drass Island arc in the red. And this was an island arc, an intra-oceanic island arc that lay between India and Asia prior to the collision of India and Asia. Okay, so here is a satellite photograph of the Himalaya taken from the space shuttle. As the space shuttle comes into the Earth's atmosphere, it comes in upside down. So here is the tail fin of the space shuttle, and we're looking, it's roughly over Kathmandu, and we're looking west along about 2,000 kilometers of the mountain range. And you can see all the snow-covered peaks are bounded by, in the green lines, the main central thrust at the bottom and the South Tibet detachment normal fault at the top. So there's two major tectonic processes that I'll be talking about a little bit. One is the continental extrusion hypothesis, which is where the thickened crust of Tibet is moved eastwards out of the way of the Indian indenter, bounded by these big crustal scale strike-slip faults. Karakoram fault in the southwest, Altintag Kunlun fault in the north, and various faults along the Indus suture zone to the south. The second major process is one of channel flow, which is the orange arrow. And channel flow is the ductile extrusion of the very hot, partially molten, metamorphosed middle crust of India, bounded by the main central thrust below and the South Tibetan detachment above. So those are the two major tectonic processes that I'm going to cover in parts of this talk. Okay, so to go back to square one, India, the Indian plate, was part of the southern Gondwana continent, so it was plastered on to South Africa, Madagascar, and Antarctica. And by looking at the seismic and the magnetic stratigraphy of the Indian Ocean, we can unwind time and reconstruct the northward drift of India from when it separated from Africa, Madagascar, and Antarctica approximately 120 million years ago. And then it collided with Asia at roughly equatorial latitudes about 50 million years ago. And that's when the Himalayan orogeny started. So prior to the collision, there was quite a lot of stuff going on in the Tethyan Ocean. And ophiolites are the indication of what the Tethyan oceanic crust and mantle looked like prior to the collision of India and Asia. In the Himalayas, we have several ophiolites, and by far the best one, which is the most complete one, is the Spontang ophiolite, which is in Ladakh, in the Indian Himalaya to the north. And on top of the Ladakh, on top of the Spontang ophiolite is an island arc, a small-scale island arc, which we call the Spong arc, 88 million years ago. This is from uranium-lead dating of the arc volcanic material on top. Yeah. And we have to have two subduction zones, northward dipping, one beneath the Spontang ophiolite and the Spong arc, and the other one to the north between the Drass, beneath the Drass Kohistan island arc to the south. Both of these require subduction zones beneath them. Excuse me. And they were both placed onto the passive continental margin of India prior to the final collision. So then that all happened before the closure of Neo-Tethys. How do we know when Neo-Tethys closed? Well, various geological factors, which I'll come on to very shortly. And we know that from 50 million years onwards, the whole crustal shortening and thickening process started all across the Himalayas. So the Drass Kohistan Island Arc, which is all exposed in northern Pakistan, and the Drass is just a little bit that continues into Ladakh to the north, is a very impressive island arc. It's 60 kilometers thick, which is extremely thick. It was very long lasting. It's 120 million years of magmatism. And it's comparable to arcs we see in the Western Pacific today. So like the Mariana Island Arc or the Izu Bonin Island Arc, which are the big island arcs that bound the Western Pacific today. Long lasting, very thick crust. So the upper crust is all made of calc-alkaline volcanic material, all exposed around Gilgit, Drass, and the northern Kohistan region. And these are all andesites, dacites, rhyolites, typical rocks that you see above oceanic island arcs, intruded by calc-alkali granites. The middle crust is all dominated by metamorphosed oceanic basaltic material. So we're now seeing large thickness of amphibolites, which are the Camila formation, which are the mesobasaltic ocean crust of Tethys, and again intruded by I-type subduction-related granites and granodiorites. And then the lower crust, which we never see in the modern island arcs in the Pacific, because they're obviously still buried, but we see them beautifully in Kohistan, are composed of garnet granulites, the Jijal complex, which are very high pressure and high temperature, and gabbronorites, which are the magma chamber underneath the island arc. So you can look at old island arcs like the Kohistan-Drass. This is a Upper Jurassic Cretaceous to early Eocene island arc, to figure out what is going on in the lower crust of island arcs. And you can use that to interpret what the lower crust of island arcs like the Western Pacific arcs looks like today. Okay, so how do we know when India collided with Asia? You can look at the magnetic anomaly stripes in the Indian Ocean, which is the best way to determine the northward drift of India. And you can also look at paleomagnetism. And when you look at the paleomagnetism, the southern margin of Asia, the yellow line in the north, has remained at pretty much the same paleo latitude since 120, 130 million years. When you look at the paleomagnetism in the Indian plate, the blue lines to the south, they are vastly different. They were separated by 2,000 kilometers of Tethyan ocean. And then they both merged together roughly at 50 million years. You can see on the bottom scale, 50 million years, when the Indian plate was pretty much juxtaposed against the Asian plate. Okay, so this is open to interpretation. And there are two very, very different models, one of which is published by Van Hinsberg and et al., Model B. And to account for this 2,000 kilometer discrepancy between India and southern Tibet, they proposed a great Indian basin along the high Himalayas, right the way along the Himalayan arc, separating the Tethyan Himalayas to the north from the greater Himalayas and the main Indian plate to the south. But there's big problems with this model because a lot of people have spent a lot of time mapping, sampling along the main central thrust and the greater Himalaya, and there are no oceanic rocks anywhere in the Himalayas along that line. So there is no geological evidence at all for a greater India basin. The story is much simpler. The Model A on the right proposes that the whole of the Indian plate, the Himalaya, the Tethyan Himalaya, the greater Himalaya, the lesser Himalaya, were all part of one single contiguous continental plate. And I will demonstrate to you using thrust tectonics and balanced restored cross sections that this model is correct. Okay, so as I said, the Himalayas are a very simple mountain belt. Unlike a lot of other mountain belts, you know, like the Alps or the Rocky Mountains or the Appalachians, which are very, very complicated, the Himalaya are beautifully simple. which is why it's such a great place to work. So on this diagram here shows a block diagram of the structure of the Himalayas, a very simplified block diagram. And the Indus Zangpo Brahmaputra suture is in the middle there in the blue. And that is the zone of collision between the Indian plate to the south and the Lhasa block to the north. On the Himalayas itself, we see the upper crust, which is the yellow unit, above the South Tibet detachment. That is the unmetamorphosed sedimentary rocks of the upper crust of the Himalaya, the Indian plate. And those are mostly present in southern Tibet, north of Nepal, and continuous into the Zanskar-Ladakh region in India. The next zone, the middle crust, is in that very bright purple color. That is the high Himalaya. That's all metamorphic rocks, migmatites, leucogranites, crystalline rocks. And they are bounded by the main central thrust below, the MCT, which is a thrust fault, south verging thrust fault, and the South Tibet detachment, the STD above, which is a low angle normal fault. And the simple geometry of that tells us that all of that red, partially molten, high temperature middle crust was thrust to the south, exuded to the south, extruded to the south during the Miocene. And that is the process called channel flow. The final unit is the Lesser Himalayas to the south in blue, and that is bounded by the main boundary thrust along the southern margin of the Himalaya, which runs roughly through the Siwalik Hills in Nepal, through the Chitwan region, and that is the active boundary of the Himalayas today, along which India is subducting beneath the Himalayas. That's the fault which is shows all the earthquakes going off today. So when you take the stratigraphy and the paleostratigraphy of the Himalayas, it's very clear that the whole Indian plate, the whole Himalayas, was just one single plate going from the Indian craton in the south, which is all the Archean rocks of peninsular India, overlain by a very thick Proterozoic sequence in brown, the Himanta sequence, also called the Cheka in Bhutan. And this thickens towards the north. There was a very large orogeny at the end of the Proterozoic, early Cambrian, where there were a lot of granites intruded and a lot of folding and thrusting and metamorphism, which has now been mostly overprinted by the Himalayan age metamorphism. And then above the Proterozoic is all the Paleozoic section in green, which are the Cambrian up to Permian sedimentary sequences, which form a lot of the protoliths of some of the metamorphic rocks in the greater Himalayas. And that's overlaying the very thin orange line there is the Panjal trap volcanics, which are the Permian rift-related volcanics we see in the western Himalayas all around Kashmir. And that indicates the Permian breakup of Gondwana. During the Permian, all the supercontinent of Gondwana broke up with a lot of basaltic intrusions, and they are particularly well exposed around the Kashmir Valley. And then overlying the Permian volcanics, Panjal Trap is the Mesozoic in dark blue. These are all the passive continental margin sediments of northern India, which are the same all the way along the Himalayas, all the way along southern Tibet, Zanskar, Ladakh, even very similar to the northern passive margin of the Arabian Plate in Oman and the Zagros Mountains in Iran. So the bottom part of this diagram shows very simplified stratigraphic profiles through each of the main Himalayan units. And you can see that the Neo-Proterozoic unit, the top of the brown, is continuous all the way across from the Lesser Himalayas to the Greater Himalayas, to the base of the Tethyan Himalayas, the Fei Formation in Zanskar. So there is absolutely no evidence of any oceanic material, no suture zone or anything along what this greater Himalayan basin was proposed, along the main central thrust in particular. Okay, this is just a section of my new map. It's all hand-colored. It's being drafted at the moment, so I'm afraid it's not it's not pristinely drafted yet, showing the main units here. And you can see that the Kashmir Basin is in the bottom left, and in brown along the base we have the lesser Himalayan, pretty much unmetamorphosed sediments. These are very old. They're Proterozoic and Paleozoic mostly, overlain by a few younger rocks at the top. And they are overlain by the main central thrust, which carries all the high-grade metamorphic rocks. These are all in green. The dark green are the upper part of the Greater Himalayan sequence. So these are all kyanite, selimonite grade gneisses, migmatites, leucogranites, crystalline rocks that form most of the high peaks of the Himalaya. And then above the green is the South Tibet detachment. In this part of the Himalaya, it's called the Zanskar shear zone, which is a northeast dipping low angle normal fault, which puts the sedimentary rocks of the upper crust, the blue, the Tethyan sediments, above the metamorphic rocks in green of the Greater Himalaya. And then north, you can see the Spontang ophiolite, the little green klippen in the middle, right in the middle of the slide. That is the abducted ophiolite. And because ophiolites were the highest thrust sheet, they formed the highest mountains in Zanskar, and they're all very poorly preserved along the rest of the Himalayas. In the east, you have the Somarari klippen, which is one of the North Himalayan domes. These are an extension of the Greater Himalayan sequence that pops up just south of the suture zone. And then you also see on this slide the granites of the Ladakh Gangdesi belt in red, which go all the way from the Nanga Parbat syntaxis all the way along the Himalayas to the eastern syntaxis. These are the Andean type granites that form the southern margin of Asia, subduction related granites. You can also see the Karakoram fault, which is the big strike slip fault that goes northwest to southeast and connects the Indus suture zone in the far bottom right up to the Pamirs, which are off screen above to the top left. Okay, next slide, please, Anurag. So the whole story of the Himalayas starts off with the deep subduction of the leading edge of the Indian plate. And these eclogites have been dated at between 55 and 47 million years, which is pretty much the timing of the withdrawal of the Tethyan Ocean and the collision of India and Asia. So these rocks are all exposed in northern Pakistan, in the Kagan region, and in northern Ladakh, the Somarari region, and they are immediately south of the Indus suture zone. They're all rocks belonging to the Indian plate, and they are all metamorphosed to extremely high pressures. 28, 29 kilobars is equivalent to 120 kilometers depth in a subduction zone. The eclogites here are actually metamorphosed Panjal trap, which are the Permian volcanics, and they've been taken down the subduction zone pretty much at the time of collision. Some of them even have microdiamonds in. They all have coesite and high pressure pyroxenes and high pressure garnet. But these rocks do not tell us anything about the timing of plate collision, because in Oman we have very similar eclogites beneath the Sumail ophiolite, which was the final thing that happened during ophiolite abduction. So these rocks in the Himalayas can be either related to the final phase of abduction of the Spontang ophiolite or the very first phase of continental collision. When you look at the pressure temperature paths here, these are rocks we collected from Pakistan, Kagan Valley many years ago. You can see pressure on the right-hand side of the graph going up to 30 kilobars. And temperature along the bottom axis there going up from 400 to 800 degrees centigrade. You can date these rocks using any of the radioactive minerals, zircon, alanites, thorites, titanites, rutile. And uranium lead dating is the only way to date these rocks with any accuracy. potassium, argon, rubidium, strontium is very inaccurate, and it will only give you a cooling age. It will not give you a timing of high pressure metamorphism. So the two minerals we dated here, allanite and zircon, have extremely high closure temperatures, 700 degrees or thereabouts. And you can see that the ages are about 46, 47 million years old. The pressure and temperature estimates are from garnet and pyroxene thermobarometry. And you can see that the titanite and rutile ages, which are the lower closure temperature ages, are very similar, almost overlapping, 46 million years. So that tells us that those rocks went from about 100 kilometers, 120 kilometers depth, up to within 20 kilometers of the surface of the Earth within 1 million years. That means that these rocks were subducted and exhumed very rapidly back up the same subduction zone. Okay, so the first thing that happened was the ultra-high pressure metamorphism of the Himalayas. This is a restoration of the whole Himalayas, very, very simple one. Each one of these sections latches onto the side of the other one. So on the top panel, we have the Indian Shield to the left, to the south, and you can see in red the traces of the restored main boundary thrust, main central thrust, and then the middle part of the panel there, the middle panel shows us the Greater Himalayan sequence metamorphism, and the Tethyan Himalaya in the bottom panel, which is the passive margin of India going off into the Tethyan thrust sheets that underlay the Spontang ophiolite. And this is a restoration to about 50 million years immediately prior to the collision of India and Asia. Okay, so how do we know, how can we tell when India and Asia collided? There's various ways you can do it, paleomagnetically, detrital zircons, but none of them are particularly accurate. The most accurate way to do it by far is to look at the stratigraphy and the sedimentology of the Tethyan zone. And when you do that, this photograph at the bottom is a mountain in South Tibet, Jepuri Shan. The white rocks are all marine limestones. They are full of fossils, microfossils, which give you a very, very precise age. The dark rocks above them are all continental red beds, so fluviatile, formed in rivers, or lacustrine, formed in lakes, but on continental crust. So the transition from the white to the dark rocks gives us the transition from Tethyan sedimentary deposition to post-collisional continental deformation. And the youngest fossils we pulled out of those rocks are belong to foraminiferal zone P8, which is the lower Eocene, and the age of that is 50.5. So we know that the final marine sediments everywhere along the Himalayas are 50.5 million years old, early Eocene, and they have exactly the same age in the Waziristan on the Pakistan-Afghanistan border, in Ladakh in India, and in South Tibet. So there is no diachronaceae, it's a head-on collision, and by 50 million years there was no more oceanic deposition anywhere between India and Asia. Okay, a few field photographs. So the bottom left photograph shows you the nummulites, which are these foraminiferal zones. They're about the size of your thumbnail, and they are very, very well known from everywhere in the world. They're extremely well dated, and those are the rocks, the fossils that give us the age of 50.5 million years, the age of sedimentation of that strata. And the two photographs on the right show you the same marine to continental transition. The first one is in the Zanskar River Valley in Ladakh, and the next one is high up in the Zanskar Range, where the limestones have been folded isoclinally, and the red rocks are the red Chulangla red beds, which are the continental rocks that overlie them stratigraphically. The top left picture is a view looking right along the Indus Suture zone in Ladakh. Asia is on the north to the left, and India is to the right. And you can see that there's smashed up ophiolites down there in the valley, the Indus molasse, and there's turbidites and cherts. These are all the deep sea sediments, Mesozoic, that were deposited in Tethys prior to the collision of India and Asia. That photograph is looking east towards Leh. Okay. When you have mapped the whole of the Indus Basin in Ladakh, you can reconstruct it. And this is a simple reconstruction of the molasse basin profile. And what we're looking at here is all the rocks of India folded and thrusted to the left, and the Asian margin, which is the Ladakh granites, the Andean type granites, on the right. So in the boxes are all the ages from uranium-lead ages of zircon ages from the granites, 57, and the youngest Lucca granites there are 47. And they're overlain by these sandstones, conglomerates, and rocks formed in the molasse basin. So the other ages in the brown and the conglomerate bands are all detrital zircon ages, which tell you the age of the sedimentation. And they go back as far as the age of collision, and they go right up to very, very young in the Miocene. The two ages in blue, the Sunda, are the Paleocene limestones that are the younger sediments in the Zanskar range, and the numalite limestones, 50.5, are the ones I've just shown you from Ladakh. So those are the youngest marine sediments anywhere in the Himalayas, and it was the same all the way along. Okay. A few pictures of what these rocks look like. This is what the Indus molasse looks like in Ladakh. This is the Indus River in the foreground with one of the beautiful Tibetan monasteries there. This is to the east of Leh. And you can see that the whole thing is backfolded. Those big banded rocks there are the big Hemis conglomerates. And these are spectacular conglomerates which show dominantly material eroding from the north, from the Asian margin. So they're mostly granites and volcanics. Some from the south, which are dominantly limestones. Some from the suture zone, which are peridotites and Lamayuru type sediments. Okay, so that's the Indus suture zone. We're now into the northern margin of the Himalayas. We're going from north to south across the Himalayan margin here. This is what the northernmost ranges of the Himalayas look like. This is in Zanskar, in Ladakh. And all of those mountains are in the Mesozoic limestones, the unmetamorphosed upper crust of the Himalayas. And what I've done here is just trace around the folds. So the yellow lines are tracing around bedding in the folds, and the red lines are where the folds have detached to become thrust faults. And this is the mechanism of how you thicken the crust, how you shorten the crust to make a Himalayan type orogeny. So these limestones are all Jurassic and Cretaceous. They were obviously deposited flat. They've now been shortened by hundreds of kilometers and thickened to tens of kilometers. This is the uppermost crust. So when we talk about the metamorphism soon, imagine this fold structure also happening in the lower crust. And that's when, as you thicken the lower crust, you go down, increasing pressure and increasing temperature, and that's when you superimpose metamorphism on these rocks. Okay, here's another picture taken along the Zanskar River in Ladakh, and these are the Triassic, sorry, can you go back? Yeah, these are the Triassic rocks, unmetamorphosed sedimentary rocks, and again, yellow is just tracing around bedding, and the red are detachment faults. And you can see from these rocks that we're looking at hundreds of kilometers of shortening when you look at those structures over the entire northern part of the Himalayan range. And you see the same structures in southern Tibet, north of Nepal. Okay. Somebody's got their microphone on. So, okay, a few more field photographs here. The Hemis conglomerates in the middle on the right, you can see those big boulders of Ladakh granites. These are hornblende biotite granodiorites. and they are overlain by the molasse deposits. The bottom right photograph shows the Indus molasse sitting unconformably on top of the Ladakh granite on the northern margin of the suture zone in Ladakh. And the middle photograph on the left shows you the actual transition from marine sediments on the right to continental sediments on the left. And you can actually put your finger on that contact. The blue line is the divide between the last marine sediments on the right, the Nummulitic limestone, and the oldest continental sediments on the left. It's very, very spectacular. Okay, so I spent many, many years, started working in the Himalayas in Zanskar, Ladakh, and I spent 4 or 5 years mapping the whole of the Zanskar Himalaya and the Indus Suture Zone. And I started having PhD students in Oxford working on there. And we were in Ladakh one day, and I had this huge blank on the map right in the middle of the Zanskar range. And you couldn't get anywhere near there in summer. The mountains are too steep, the valleys too deep. And the local people in Padam said, oh, you need to come back in January when the river freezes and you can walk on the river. So in the late 90s, we went there in January, and we spent 1 month walking on the frozen river from the Indus Suture in the north down to the Zanskar shear zone in the Himalayas to the south. And here's a few pictures of that trip. It was an absolutely fantastic trek. We were 8 days camped on the ice. The person there is standing on ice about 6 inches deep, 6 inches thick, and the river was fast flowing. So the top right photograph, you can see Ben Stevenson, my student, scrambling around the edge there on the ice, which is, you had to make very sure you weren't going to fall through the ice because you were carrying 20-kilo rucksack and your friends couldn't haul you out. You'd have swept down the river. So very dangerous, but very fantastic trek. And we managed to map along there as well. Okay, so that is the northern Tethyan Himalaya. We're going on now to look at the crystalline rocks of the greater Himalaya. Now, these rocks extend into northernmost Nepal. And the figure on the left shows you the sequential diagram. So the top one is the age of ophiolite abduction, which is late Cretaceous Paleocene. The next one down shows you the collision around 50 million years when the two continental plates met, and the blue is the last of the Tethyan oceanic rocks between the two plates. And the third one down shows you the folding, thickening, crustal shortening that I've showed you pictures of just recently. And the last diagram on the bottom cross-section shows you the Miocene channel flow, which I will talk about in a minute. Okay. So how do you explain all of this? First of all, you have to distinguish between sedimentary deformation of sedimentary rocks, like I've shown you in the Zanskar shelf, folding, thrusting, crustal shortening, crustal thickening. And then when you thicken the crust so much, you metamorphose the base of it. You're increasing temperature, you're increasing pressure. And in that middle diagram, you can see the dashed red lines are metamorphic isograds. And they are increasing in pressure and temperature as you go down structural section. So in that middle diagram, you're going from unmetamorphosed sedimentary rocks in light green, and then you're going through a series of isograds. Isograds are lines of the same metamorphic grade, and you can map them by the mineral assemblages. So the first one is biotite, and as you increase up pressure and temperature, you go through the Barrovian metamorphic sequence. So we're looking at biotite, garnet, staurolite, kyanite, and sillimanite. All of those abbreviations in the middle diagram show you the increase of metamorphic grades as you're going structurally down section. And then when you've locked in those isograds during the Miocene, the whole temperatures are increased that you're actually starting to melt, partially melt the middle crust. And these are where you get sillimanite grade migmatites. Migmatites are mixed rock. Half of them are leucosomes, which are melts, and the other half are restites, which are the metamorphic equivalent. So restites are all biotite, sillimanite, garnet, schist, and the leucosomes are all garnet, tourmaline, biotite, muscovite, leucogranites. And as soon as you start to melt parts of the crust, it reduces the viscosity and it extrudes out to the south. So all of this was determined by mapping of metamorphic isograds back in the late 80s, early 90s, where we first discovered that the metamorphic isograds along the South Tibet detachment at the top of the Greater Himalayas were right way up. The bottom diagram here I'm looking at now, the whole core of the Himalayas is this partially molten migmatite zone, and around the main central thrust at the bottom of the diagram, the isograds are all upside down, inverted. So the whole of the metamorphic isograds along the main central thrust, along the entire Himalayas, are upside down. As you walk north across the main central thrust, you are increasing metamorphic grade as you go structurally higher. And as you go north to the South Tibetan detachment, it's the opposite. You're going from high grade rocks up structural sections to progressively lower grade rocks, then the big detachment, and then you're into the unmetamorphosed sediments. Okay, so that's how you create inverted metamorphism. Right, we're now in Nepal. I'm sure you recognize this. You have the most beautiful mountains anywhere in the world in your lovely country. And this is the peak of Dhaulagiri in the west. The Kaligandaki is the valley that divides Dhaulagiri from Annapurna. This picture was taken from near Poon Hill. And on the bottom, you can see the kyanite, which is the beautiful blue crystals. Kyanite and sillimanite are both aluminium silicates, Al2SiO5. Kyanite is the high pressure polymorph. Sillimanite is the high temperature polymorph. And both of those show initial partial melting, producing those little melt pods at pressures around 10 to 12 kilobars in kyanite, and at slightly lower pressures in sillimanite, but slightly higher temperatures, which is the main period of when you're producing the leucogranites and channel flow is happening. So you can see in the top diagram that Annapurna and Dhaulagiri are about the only two 8,000 meter peaks that are within Tethyan sediments. Dhaulagiri is made of Cambrian and Ordovician limestones and dolomites, dominantly unmetamorphosed. The South Tibet detachment cuts right through the bottom of the mountain, and the whole of the top of the sequence there has been faulted out. And the whole section down the Kaligandaki all the way down shows you the inverted metamorphism. So we're going from sillimanite at the top to kyanite to garnet to biotite. And then the high strain zone of the main central thrust is beneath the biotite grade in the south. Okay, so here's a blow-up picture of Dhaulagiri. And I've got three samples here that we did pressure temperature work on. So the bottom one is the kyanite gneiss in green. That is formed at about 10 to 12 kilobars, which equates to about 35, 40 kilometers depth. The next one up is a clinopyroxene tremolite K feldspar marble, very high temperature crystalline marble. And that was formed at around 9 kilobars. And then the next one up is the unmetamorphosed Cambrian sediments at the base of Dhaulagiri. And you've got to somehow figure out a way to get all three of those juxtaposed right next to each other. As you trek down the Kaligandaki, all of these samples came from right along the main trail down the Kaligandaki. Okay, so what we're going to do now is restore that section to, oh, sorry, I'm slightly out of sequence here. But anyway, there's a geological map of the Nepal, South Tibet Himalayas. And you can see that the green is all the high-grade metamorphic rocks of the Greater Himalayas, and the Lesser Himalayas are in brown at the bottom. As you cross over into Tibet, you're into the blue, the Tethyan upper crust, and these circular rocks within the Tethyan are the North Himalayan domes, and this is the northernmost extension of the Greater Himalayan sequence. They have the same rocks, the same structure, and a lot of them the same ages. So it's just the South Tibetan detachment coming up in a big domal structure. And then around the Zangpo Valley in Tibet, the Indus Suture zone, and then to the north of that in red is the Andean type granites. Okay, so I've done a lot of work in the Mount Everest area both in Nepal and South Tibet, and I published this map back in 2007, which is one of the best profiles to look at the high-grade metamorphic rocks of the Greater Himalayas, partly because the mountains are so high, the valleys are so deep, you get a complete three-dimensional structure there to map on. And I've still got a few copies of this map, which I can bring out with me when I come to Nepal in October, November. This is what Everest looks like. Now, I'm sure everyone has heard of Everest. It's all the crazy climbers go there now for all sorts of reasons. I go there to map the geology, but I have two friends who guide up there, and they have base camp sites. So this is the base camp site in the Khumbu Valley in Nepal, and I used that as a base to map around the valleys there. A lot of this was done in the late 90s and 2000s, so before the kind of mad rush of climbers that we see today. But this picture is taken from the peak of Lingtren, looking right down onto the Khumbu Glacier. Where it says base camp, there's about 100 tents scattered in the moraines there. And the route goes through the icefall, very dangerous icefall up to the Western Cwm. And this picture is now taken around the same level as the top of the icefall, looking at the peak of Lhotse straight ahead and Nuptse to the right, and the summit of Everest looking above the West Ridge, top left. So that's the sort of country we're looking at. This is a Google Earth image to show you that the South Tibet detachment, which is a very low angle normal fault dipping to the north, is incredibly well exposed. The Rongbuk Valley is just one of the most spectacular valleys to map this low angle normal fault. And combining that with the main trek up to Everest from the south, from Lukla up to Namche Bazaar and Solakhumbu, by combining that section in Nepal to the Rongbuk section in Tibet, we managed to get a complete three-dimensional view of the whole GHS. Okay, so I'm going to show you a cross-section now through the summit of Everest using both the Khumbu section in the south and the Rongbuk section in the north. And what the cross-section shows you is the Chomolungma detachment, the low-angle normal fault, cuts right through the summit of Everest, and it extends all the way down to the Tibetan Plateau. So you can actually physically map it, walk on it for 70 kilometers from Everest northwards until it disappears under the Tibetan Plateau. And this is a lateral section, a west-east section showing the same thing. The green is the Everest series schists, which are beneath the Chomolungma detachment. And then there's another normal fault, the Lhotse detachment, which is really the upper limit of all the leucogranites and the high-grade metamorphic rocks below. So you can you can restore the Greater Himalayan section using both protolith ages, uranium lead ages, detrital zircon ages, and metamorphic ages to get the depths. So what we're looking at here, the protolith of the Greater Himalayas is dominantly Proterozoic, and it goes up to Cambrian Ordovician on the summit of Everest. The leucogranites in red are dominantly derived from melting Neo-Proterozoic sediments, which are equivalent to the sillimanite grade gneisses we see structurally below Everest. Okay, so I had two PhD students working on pressure, temperature, time paths on those two profiles, Micah Jessup, and this is far too detailed to go into here, but I will summarize it in the next few slides. And the other student was John Cottle, who did a lot of work on uranium lead dating. So each one of those black dots shows samples that we've got on both the Nepal side and the Tibet side, in which we determine pressure, depth, temperature, and time over all of those samples. This is the section in the Zakhachu in Tibet, north of Everest, which is a profile through the Greater Himalayan sequence north of Everest. You can see the leucogranites in red at the bottom. It's a big, thick shear zone at the top. I'm running a little bit short of time, so I'm going to skip quickly on. And in summary, Everest is very similar to the Zanskar region to the west. So we have the crustal thickening, which is from 50 to about 32. This is the peak of kyanite grade metamorphism. Decompression to sillimanite grade metamorphism, 32 to 16. This is the timing of channel flow and formation of the Himalayas, going all the way down to the onset of glaciation, which is what we're seeing today. So it may be surprising to you that the highest mountain on Earth is cut by two normal faults, but this is the structure of those normal faults. So right at the top of Everest, we have Cambrian Ordovician sedimentary rocks. Below that, we have the Everest series, and below that, we have the leucogranites. This peak, Gaichin Kang, is to the west of Everest, just below 8,000 meters, so nobody goes there. But it shows these two low-angle normal faults like somebody's taken a bread knife and sliced it through. Very, very spectacular. Okay, next one, please, Anuraj. We go on to the next.
Its internet is
Seems to have lost. Sorry? Ah, okay. So this picture here is looking straight up the north face of Everest from the Tibet side. The Chomolungma detachment is the yellow line. You can see that the top is unmetamorphosed Ordovician limestones, and these still have little tiny fragments of trilobites and crinoids in them. The yellow band below that is Cambrian calcsilicate and marble, which is clearly a metamorphic rock. Below that is the Everest series. And these are two thin sections. The one on the left was collected by Ed Hillary, the great man himself, on the very first ascent, 29th of May. And that is clearly a sedimentary rock. The one on the right is collected from the yellow band by Charles Evans on the first attempt. That's clearly a metamorphic rock, and the Chomolungma detachment lies between the two. This is a thin section of a rock from the summit of Everest, and it shows a crinoid ossicle in the top. A crinoid is a sea fan, a sea lily, and it has a single crystal of calcite which forms the stem. And that is a cross-section through one of these crinoid ossicles. The fragment at the bottom is a trilobite fragment. And these were formed on a tropical beach 470 million years ago, and they are now sitting at 8,800 meters on Everest. This is taken from the Nepali side, looking from Lhotse Nuptse across to the south face of Everest. The yellow band, the Cambrian limestones, are right at the top, and the Chomolungma detachment separates the summit limestones from the metamorphic rocks of the Everest series below that. The Nuptse detachment is the red line that really is the top of the leucogranites that form all around base camp to the south. And you can match the Cambrian Ordovician stratigraphy all the way along the Himalayas to show that the Everest rocks here are very comparable to Cambrian Ordovician rocks we see in Zanskar and Ladakh. To the north of the South Tibetan detachment, this is as you drive into Everest along the Rongbuk Valley, we're looking at the same sedimentary rocks as we saw in Zanskar. Here are the blue lines are just tracing around bedding, and the yellow lines are the axial planes of the folds. So the structures are very similar along strike. And then the peak of Lingtren is just to the west of base camp. This is a huge leucogranite sill that overlies sillimanite grade gneisses right above the Everest base camp. And those leucogranites on Lingtren you can map all the way around Everest, round to Amadablan, and all the way down the Rongbuk Glacier. When these sill complexes reach the surface, they balloon out. So this thing actually looks like an intrusive pluton, but none of the leucogranites in the Himalayas are plutonic. They're all sill complexes, which as they decompress, as they're coming up towards the surface, balloon out into this sill. This is the peak of Nuptse. To the south of Everest in Nepal, this is the beautiful mountain of Amadablan. You can see the leucogranite. This is the Everest leucogranite intruding in from the north, and it's feeding magma up via these dikes, which are bent over into the Lhotse detachment above that. The outcrops up there in the high mountains of Nepal are really absolutely spectacular. And this is a peak photo from a friend of mine, Jamie McGuinness, from the summit of Everest, looking straight down the Rongbuk Glacier to Tibet. The Chomolungma detachment in Chaoyu clips the summits of Chaoyu and Gaichungkang. All the mountains below that are sillimanite gneisses and migmatites. This picture here is from the summit of Everest, again looking west. Everything you can see there below is leucogranite and sillimanite gneiss. Okay, so one of the most spectacular outcrops of all was this outcrop here in the Kangshung Glacier. This is right on the east side of Everest on the Nepal-Tibet border. You actually have to approach it from Tibet. It's the top of the Arun Valley. And here you see huge boulders of earlier formed biotite sillimanite gneiss completely enclosed in the main Everest leucogranite. I'm running very short of time, so I'm going to skip very quickly on here. Next one. This is the Rongbuk Valley detachment showing the low angle normal faults. They're very a lot of people, geophysics people, for example, don't believe them because you never see earthquakes on low angle normal faults, but they are absolutely undoubtedly there. We're finding them all over the world now in core complexes in the Aegean Basin and Range, all places like that. So they are absolutely definitely there, and they have huge jumps of pressure and temperature across them. So we dated a lot of these leucogranites. The earliest ones are in the Rongbuk Valley are 16 million years. Those have deformed and folded and cut by the latest set of leucogranites, which are younger, only just younger, 15.6. So we're looking at all of these granites intruded within 1 million year, and all of the ductile fabrics right below the South Tibet detachment also forming in less than 1 million year. This is probably the clearest slide to show you that these three sets of leucogranites, set 1 in green, are interfoliated with the ductile fabrics in the sillimanite gneiss. They are cut by the less deformed set 2 dikes, 15.6, and the final set of intrusion dikes are 15.4. These are completely undeformed and they cut across all of the ductile fabrics, and all of them were formed within 1 million years, which is incredible. This is as high as we got on the north side of Everest, just below the South Col. Nuptse detachment in red, that marks the upper limit of the leucogranites. And looking across the valley at the Rafula, which is where they first discovered Everest more than 100 years ago, the climbing route up Everest from the north. And the outcrops up there are really spectacular. And I had another student, Mike Struhl, working on the Makalu leucogranite to the east of Everest. This is a similar leucogranite, 16 to 15.6 million years old, but it's composed mostly of cordierite. So it's a slightly higher temperature leucogranite, and you can see that it's younger. It cuts all the early Everest type granites on the left there. And the Makalu leucogranite is absolutely amazing. This is one boulder, the size of this room, with 6 different cross-cutting phases of leucogranites. And from the oldest green, so the youngest number 6 in blue, less than 1 million years separates those. And you can combine all this data into a model. This is the channel flow model, which is the ductile extrusion of the partially molten middle crust, separated, bounded by the main central thrust at the base and the South Tibetan detachment at the top. And again, you can play good games using pressure, temperature, and depth data here. These are the leucogranites forming at a very conservative 15-20 kilometers depth. And you can see that the pressures for kilobars equate to a depth of burial approximately 100 kilometers north of where we see them today on the Everest base camp. So the ductile channel flow extrusion was a minimum of 100 kilometers. And when you combine that with the seismic profiles from South Tibet, where they image bright spots on the in-depth profile, these are leucogranites forming today at similar pressures and depths to the Himalayan leucogranites 20 million years ago in Tibet. Okay, here's a very simple diagram of channel flow showing what the fabrics are looking like. All of the top fabrics are all top to the north, which are actually bottom to the south. All of the colored material there is partially molten, so migmatites, leucogranites, and they are showing right way up metamorphism at the top, inverted metamorphism at the bottom, and at least 100 kilometers of southward extrusion of the channel. And then the low temperature geochronology is also interesting because it's actually only a bit younger than all the granite, which suggests that the mountains have been high ever since at least 24, and probably as long ago as 30 million years, you've had high topography along the Himalayas. Is Everest still going up? Well, yes, it is. We've got GPS stations now on the summit, all the way down to Namche Bazaar and all the way across Nepal. And we know that the vertical uplift is about 3 millimeters a year. So Everest is still going up. It's being jacked up from underneath by these thrust faults along the main boundary thrust, which is where you're getting all the earthquakes. Okay, I'm going to skip all this section here because I've run out of time. This is a view of the eastern syntaxis. We've done a lot of work on the western syntaxis in Nanga Parbat, and this is the most incredible mountain because it's undergone the whole of the metamorphic history of the greater Himalayas, but we've also got uranium-lead monazite ages as young as 0.7 million years. This is Pliocene, Pleistocene, partial melting. These are the youngest granites ever dated anywhere in the Himalayas, and they're now at 8,000 meters on Nanga Parbat. So we're looking at incredibly fast uplift exhumation rates. This is what the rocks look like. The big green minerals there are cordiorites. So we're looking at cordiorite, sillimanite, very high temperature, partial melts, less than 1 million years old. And I think these could be a good indication of what the lower crust of the Himalayas looks like in the unexposed parts beneath the northernmost part of Nepal, the southernmost parts of Tibet. Okay. I think I'm nearly there. So yes, the Himalayas are absolutely spectacular divide. The northern slopes look like this on the left. This is the north face of Makalu. There's 4.5 kilometers of relief from the top of Makalu down to the Kangshung Valley. And this is on the main road going south towards Kadari in Nepal with all the monsoon waterfalls coming off. So it's very active, young uplift still going on today. 2 crustal scale cross sections here. This is using both surface geology and geophysics to constrain the lower crust. And all of these in-depth and high climb experiments, seismic experiments, seem to agree that the Indian lower crust must go at least underneath Tibet as far as the Bangong Suture, if not all the way across to the north. So the under-thrusting Indian crust is all the Archean shield. There are no Archean rocks anywhere exposed in the Himalayas. You have to balance that with the Proterozoic and younger rocks in the Himalayas, and the only place you can do that is to underthrust the whole of Tibet. Okay, I'm not going to go into receiver functions now. Let's finish off with the Gorkha earthquake, which I'm sure you're all familiar with. The epicenter went off where the red star is, and 12 days later, the second big aftershock went off the orange one in underneath Everest. So this was a huge earthquake, but it was nowhere near big enough to accommodate all the stress that is being built up there to the south. And the most worrying thing is you can see on the lower diagram, the cross section, the rupture break was underneath Kathmandu going north under the Himalayas. Those mountains to the north of Kathmandu rose by 1.1 meters in 2 seconds, the whole mountain range, and it shortened. The big problem was that all that stress should have gone up to one of the thrust faults in the south, in the Terai, and none of those thrust faults broke. So it means that all that stress is still down there, just waiting to go off anytime soon. And I'm sure you've seen all these pictures of the destruction in Kathmandu. And I'll leave it with my book. I've just finished another book actually on the Nepal earthquake, which hopefully is coming out next year. But this is the one that describes all the Himalayan material that I've covered through this talk. So thank you very much for attending. It's very nice to see you even remotely. A big thank you to Isha and to Anurag for operating all the PowerPoint remotely. And that's it. Thank you very much.
Thank you so much, Professor Mike, for this wonderful presentation. And I am seeing our faculty advisor, Assistant Professor at Tribhuvan University, Dr. Deepak Samlagai. I would like to welcome him in the program. And if anyone has questions, please, the floor is open for you. Please open your mic and you can ask the questions to Professor Mike.
Sure. It's probably too much material to cover in my talk to think of a question, but I'm very happy to answer questions anytime or discuss things on email or whatever. I come out to Nepal every year, so hopefully I will be out mostly in November this year, and I hopefully will call in and to Tribhuvan and maybe see you at some stage then. So thank you all very much for attending. And
I guess there is no question from anyone. So I would like to call our faculty advisor, Dr. Deepak Samlagai, for the remarks of the session.
okay.
Hello?
Hello, Susan.
Yes, sir, you are audible.
Is it audible?
Yes, sir.
Hi, Mike. Thank you very much for your insightful talk. Namaste. So
Namaste.
happy to, yeah, I was quite disturbed with my kids. It's bed to time to bed. But anyway, it's really a grateful talk, and I hope that students enjoy a lot. So yeah, so this is really good. And some of the map that you have donated to our department, we are using this map in our geology courses. It's still there, some of the map, every section. These are
Sure.
the really nice map that we can show to our student to motivate more on the high Himalayan section. Yeah, so thank you very much for your talk. And this is a small student group that is Society of Exploration Geophysicists, Tribhuvan
Yeah.
University chapter group. And these young undergrad students are really active, and they are organizing several talk program from the Nepali professor or the any professor from abroad. So happy to see you, and I hope so if you have a time in November, so please visit to our
Sure.
department. So our department is in Trichandra and Clock Tower.
Yeah.
So, but
Yeah.
that building was badly damaged, so we are moved to another building on the other side of the road.
Okay.
So, thank you very much, Mike, for your insightful talk.
My pleasure. Thank you very much indeed.
Thank you so much, Deepak sir, for your remarks. And for the closing sessions, I would like to express my thankful appreciation to Professor Mike and all the participations over here. And we are truly looking for the your physical appearance in the Trichandra Multiple Campus and look for the physical sessions in our campus. And for the group pictures and the screenshots, please open your camera if possible, every participants. You can close the screen share, Anurag. And we are truly grateful to Professor Mike for understanding and cooperating with us despite of technical issues.
Ah, good to see faces. This is not as good as in person. A nice photograph in person, much better.
So let us know, Mike, when you are coming. So you'll organize one physical your guest lectures in our
Yes,
department. So
I
let
will.
us know. Yeah.
I will. Yeah. No, thank you very much for the invitation. I look forward to meeting you.
Okay, we look forward to meet you as well.
Good.
Thank you so much for your time.
Okay. Thank you, Isha. Thank you, Anurag, for forwarding the slides as well.
It's our pleasure.
Okay. See you in Kathmandu in November, hopefully.
सिधै होइन त
सक्यो सर
हजुर सर
ल ल एकदमै राम्रो काम गर्यो माइक सिरियलको चाहिँ यसरी लेक्चर सुन्न पाउनु चाहिँ मैले पनि केही टकहरू चाहिँ सेमिनारहरू नसुनेको हो तर यसरी एकदम डिटेलमा अब अलिकति कन्टेन्ट अलिक इनडेप्थ कन्टेन्ट भएकोले अलिकति बुझ्न चाहिँ गाह्रो भयो होला धेरै कन्टेन्टहरू थियो अलिकति मतलब अन्डर ग्राड लेभलमा जति जियोलोजी पढेको हुन्छ त्योभन्दा अझ बढी थियो त्यसमा चाहिँ होइन एनिवे एकदमै राम्रो अब तिमीहरूले चाहिँ उहाँलाई चाहिँ एकचोटि नोभेम्बरमा आउँदाखेरि चाहिँ यहाँ गर्नु पऱ्यो डिपार्टमेन्टमा एउटा है त्यहाँ
हुन्छ
बरु
सर
मिलाउँला टाइम साइम एउटा मिलाउँला ल तिमीलाई एकदम धन्यवाद यो यसरी उहाँको टक सुन्न पाउनु चाहिँ यो एकदमै रेयर अपर्च्युनिटी हो र तिमीलाई धेरै धेरै बधाई छ
थ्याङ्क यू सर
अनि अनि अर्को कुरो इन्फर्मल यहाँ सब भेला भएको